As we have previously discussed, multi-phase flows are rampant in our daily lives, and we usually see them, for example, during liquid boiling or during the opening of our carbonated beverages and other mixtures we encounter daily. In these systems, we could have scenarios involving two immiscible fluids, otherwise called liquid-liquid flows. We could also have gas-solid flows. We could have gas-liquid flows and also liquid-solid flows. In fact, we could have a scenario in which all three phases coexist. However, our emphasis today will be on solid liquid flows and what factors we have to consider when describing them mathematically. Now, I've decided to draw your attention to a more complex occurrence of multi-phase flows in industry, which is that of well drilling. The wells in question could be oil wells, hydrothermal wells, or wells that are used to assess water beneath the earth's surface. As we see here, powerful drilling machinery is used to penetrate the rock formation, leading to the evolution of rock particles. These particles must be removed with a fluid at high flow rates to maintain high penetration of this machinery into the rock. This prevents the drill pipe from getting stuck. So you can see here a classical representation of solid liquid multi-phase flow systems. Now, this is a conceptual representation of the system we have seen in the previous slide. We can see the different parameters that come into play, as the size of the annular clearance as determined by the diameters of the well bore and the drill pipe respectively. We could also see that the inclination of the well bore is an important parameter as well as the rotation of the drill pipe. Other parameters include the fluid density and viscosity as well as the particle diameter. Now, as far as the mathematical description of the system is concerned, we have to first understand what happens when a single particle interacts with the fluid by calculating the drag and lift forces using established models in literature. We can then apply this understanding to calculate the collision forces and parameters in a system where many particles are involved, and then subsequently examine the impact of a flow boundary. Now, what is the importance of developing this understanding, some of you may ask? High particle concentration in the annulus causes the drill pipe to get stuck, and this is totally unacceptable because this slows down the operation significantly. So what we want to also know is what sections of the geometry are most susceptible to increased deposition based on the calculated interaction parameters and these forces I previously mentioned. We're also interested in understanding the impact of particle shape on the transport efficiency. So we'll be looking into the details of implementing these models I described in our subsequent class.